Okay, so good evening, everyone. Uh, in this, in today's classes, we are going to solve some more questions related to your previous assignments. Okay, this is just extra additional, 2 hour sessions. Okay, so what I will do in this session is that I will just go back from some of the questions. Okay, it's just like some of the few questions which you have already seen before. We can just try to solve one or few questions from each topic just to remind it. Okay, and uh, yeah, so this is 2 hours classes. Okay, I'll try to solve like around 5 to 6 questions. Okay, then related to your similar questions which you have already seen before. Okay, uh, so I can wait for 1 minute if somebody wants to join. Okay, and then we can start. Okay, so let's start the sessions. Okay, so the first questions in today's class, what I will do is that I will not write many of the formulas and all. Okay, what I will do is that I will just solve directly the problems. Okay, related. Yeah, okay, so thank you for joining today's class. Okay, so in today's class, what we will do is that I will not again I will not again solve many questions. Okay, so what today is that we can just solve few more questions from each topics. Okay, which we have already done before. Okay, as a just a reminder. Okay, if you have any particular sets of questions from which topics that we can discuss. Okay, but at the moment, since I don't get any questions related from which topics you would love to, then maybe I can just solve again a few questions from each topics. Okay, so that will be maybe helpful to some of you. Okay, to some of you. So first of all, like I have mentioned, we will solve only questions here. Okay, and we will not um, write again all the formulas and so on. Okay, so the first questions that I will be I will solve is related to your photoelectrons, which is related to your photoelectric effect. Okay, so okay, so the question sets anyway I will upload it in the drive, so I will not write the questions in full detail. So the first question is ultraviolet light of wavelength lambda equal to 350 nanometer and intensity intensity 1 watt per meter square. Okay, is directed at a potassium surface. Okay, at the potassium surface. Now find the maximum kinetic energy. Find the maximum kinetic energy of the photoelectrons. Okay, so that is the first question. Now let's solve this one. This is pretty straightforward. Okay, so your wavelength is given to be lambda 350 nanometer, and what is the energy corresponding to this wavelength? E is equal to, you can write E is equal to h mu or h c dot by lambda. You can also write this in terms of 1.24 into 10 to the power minus 6 electron volt. In terms of electron volt, you can calculate this, and divided by 350 into 10 to the power minus 9 meter, which this is equal to 3.5 electron volt. Okay, so you use the formula E is equal to h mu or hc by lambda. Either you can substitute in terms of joules. That means h is equal to 6.6 into 10 to the power minus 34, and you substitute the speed of light, or you can calculate, we can substitute the value of hc in terms of electron volt also. That is also fine. Now we have to find out the kinetic energy. So you remember that for the photoelectric effect, you have energy h mu is equal to the work function phi plus the kinetic energy, correct? So the kinetic energy will be h mu minus of phi. So what is h mu? H mu is 3.5 electron volt minus phi. What is phi for a potassium? Phi for a potassium, you can write on the sides. It should be given to you. Phi is equal to 2.2 electron volt. So now you can substitute here 2.2. It should be equal to 1.3 electron volt. So from here you can easily calculate what is the kinetic energy, right? So I think this formula you remember. You just substitute E is equal to hc by lambda, and more importantly this formula. Okay, h mu is equal to the work function plus the kinetic energy. Okay, now set B says that, okay, if 0.5% of the incident photon produce photoelectrons, how many are emitted per second? Okay, this we have to find how many number of photoelectrons are emitted per second if potassium has area of 1 centimeter square. Okay, so that means 0.5% of your photon is incident on your on the surface of your potassium, and how many number of photoelectrons are emitted after your incident photon if the potassium has 1 centimeter square. That is the questions. So now what happens that whatever the energy, okay, whatever the energy that we have calculated here, energy is equal to energy of the photon is 3.5 electron volt. So now you know from the section A, energy of the photon is 3.5 electron volt. If you convert in terms of joules, will be equal to 3.5 into 1.6 into 10 to the power minus of 19 joule, which will be equal to 5.68 into 10 to the power minus of 19 joule. Okay, since this is the total number of photons reaching the surface, okay, now the number of photons that are reaching the sample. Okay, now, or not number of photons, sorry, this is the energy of your photons. Now the number of photons reaching the surface per unit area is, let's say I represent it as NP, which is the number of photons reaching the surface per unit area. Is NP is equal to what? Is equal to energy per unit time divided by the energy of your photons, right? Is equal to area and divided by EP. Okay, so power per unit area, you know, right? Energy per unit time, okay, which is also related to power. Energy per unit time is also related to power per unit area into the area divided by EP. So a power per unit area is given to you to be equal to 1 watt per meter square, right? Into your area is also equal to 1 centimeter square, and 1 centimeter square you can express in terms of meter square, which is equal to 10 to the power minus 4 meter square divided by your energy of your photon, 3.5 into 10 power minus of 19 joule. Okay, then from there you calculate 1.76 into 10 to the power 14 photons per second. Okay, So this is the number of photons per second. This is the number of photons per second. So how do you calculate? You just calculate what is the power which is also given to you, and the power which is equal to one intensity of 1 watt per meter square, and then from there you can calculate the number of the number of photons reaching the surface per unit area. Okay. Now if you want to find out rate, right, rate, therefore rate at which photo electrons are emitted is, Ne equal to 0.005, that is given to be the percentage of 0.5%, right, into your Np, because only 0.5% of photons reaching the surface. So this is the number of photons emitted per unit area. Then if you multiply, you get 8.8 into 10 to the power 11 photo electron per second. Okay. So now this question is the same as the one that you have that we have done long time back, okay, in the first of few lectures, few tutorials that we solve related to your photoelectric effect. Okay, so this also I use the same thing. The main formula is E is equal to, or the h mu is equal to work function phi plus the kinetic energy. Okay, so this is one of the questions. Now second question which I would love to solve is related to your Compton effect. Okay. So you remember Compton effect, the formula lambda prime minus of lambda is equal to h divided by MEC 1 minus of cos phi. Okay, I think you still remember these questions. I mean this formula. Now let's solve the question. X-rays of wavelength, of wavelength 10 picometer are scattered from a target. A. Find the wavelength of the X-rays scattered through 45 degree. Find the wavelength, that is lambda, of the X-rays scattered through 45 degree okay, and find the maximum wavelength. The second is find the maximum wavelength present in the scattered X-rays. In the scattered X-rays. Okay. Okay, so we'll the last one is C. Excuse me. Find the maximum kinetic energy of the recoil electrons. Okay, so question number A, what you have to find? You have to find out what is the wavelength of the scattered X-rays to an angle of 45 degrees. So you use this formula, lambda prime minus of lambda equal to h divided by MEC 1 minus of cos phi. Correct? And what is lambda prime? Lambda prime here is the scattered X-rays, and lambda is your incident. Okay, so lambda prime will be equal to lambda plus h divided by MEC 1 minus of cos phi. And here phi is given to be 45 degree, is already given to you. Then you will get something like 10 picometer, I will write it here, plus h divided by MEC 1 minus cos 45. Okay, and these values is equal to 10 picometer plus 0.293 lambda c, which is equal to 10.7 picometer. Okay, what is lambda c here? Lambda c is, the value of lambda c is equal to 2.42 into 10 to the power minus 12 meter. So in this case, this is a very standard, a very direct problems where you just need to use the relation of your incident wavelength lambda, incident X-rays which has a wavelength lambda, and your scattered X-rays which has a wavelength of lambda prime, and it has to scatter through your angle phi, scattering to an angle phi. Okay, or in this case the angle is given to be 45 degree, and you have to find out what is phi prime. So here lambda prime. So lambda prime is your scattered, the wavelength of your scattered X-rays is 10.7 picometer. Okay, and your incident is 10 picometer. Okay, fine. The second is that find the maximum, is given that find the maximum wavelength. Okay, what is the maximum wavelength that it can? Okay, so lambda prime minus of lambda is maximum if 1 minus of cos phi, the term this has to be maximum. Okay, because if 1 minus of cos phi, if 1 minus of cos phi is maximum, then lambda prime minus of lambda also will be maximum. So 1 minus of cos phi will be maximum if what? If is equal to 2. That means cos phi is equal to -1, because your cos phi term will go from +1 to -1. So if this +1, then 1 minus 1 will be equal to 0, then be minimum. But if cos phi is equal to -1, then 1 minus of -1 is equal to 2. That means this will be maximum. So then in that case, we get lambda prime minus of lambda is equal to h by mec into 2. Correct? And then lambda prime is equal to lambda plus 2. I can write it as lambda c, because h by mec is equal to lambda c. Okay, lambda 10 picometer plus 2 lambda c you already know, which is equal to 4.9 meter, is equal to 14.9 picometer. Okay, so this is the second. The third, or C, how do we what is the kinetic energy? Now the kinetic energy equal to h, what is the incident? Mu minus of mu prime, or hc by lambda minus of hc by lambda prime, or I will write as hc 1 by lambda minus of 1 by lambda prime. Okay, so now lambda prime is the scattered and lambda is the incident, which is equal to h 6.6 into 10 to the power minus 34 into c 3 into 10 to the power 8. Correct? And 1 by lambda, lambda is your incident, we get 10 picometer, and lambda prime is equal to 14.9. Okay, because this is the maximum wavelength that it can take, picometer. Then you substitute again, we get 6.54 into 10 to the power minus of 15 joules. You can solve this 1 by 10 picometer minus 1 by 14.9 picometer, and picometer is 10 to the power minus 12 meter. Okay, so 1 picometer, let me just write it here, 1 picometer equal to 10 to the power minus 12 meter. Okay, and finally, if you want to convert in terms of electron volt, you have to divide by 1.6 into 10 to the power minus of 19. So 6.54 into 10 to the power minus of 15 divided by 1.6 into 10 to the power minus of 19. This will be equal to what? This will be equal to 40.8 kilo electron volt. Okay, if you want to find if you want to express in terms of electron volt, then you can divide by 1.6 into 10 to the power minus of 19, and it will be in terms of your electron volt. So these questions, the first and the second questions are related to your photoelectric effect as well as your Compton effect in the first few tutorials which we have already done before. Okay, and this is just a reminder that we use these formulas very often, okay, in such questions. Now maybe I can solve now the problems number 3, which is again ahead of this. Okay, which is related to your uncertainty principle. Okay, I think you know uncertainty principle is given by your del x dot del p is greater or equal to h cross by 2. Okay, from quantum mechanics, I think you remember these relations. Okay. So now let's solve one problems related to these questions. Okay, a measurement establishes the position of a proton with an accuracy of plus minus 1.00 into 10 to the power minus of 11 meter. Okay, so that means the position of the proton is given to you to be 1.00 into 10 to the power minus of 11 meter, and find the uncertainty in the proton's position 1 second later. Also assume that V is less than C. Okay, so here what happens in this problem is that the positions of a proton is given at time t equal to 0 to be an accuracy of 1 plus minus of 1 into 10 to the power minus of 11 meter. Okay, that is the positions, and the accuracy is given to you. I mean the accuracy. Now you have to find out what is the uncertainty after 1 second later. Okay, so that is the questions. So now I think uh, you remember this question, del x dot and this relation del x and del p is greater or equal to x plus 2 by 2. Okay, so we assume that let greater or equal to h cross by 2 del of x naught. Let's assume that delta of x naught is at t equal to 0. Okay, at time t equal to 0. Now since your velocity is very less than c, then you know your delta p is equal to simply m delta v. P is equal to mv, right? So you can replace this, and so your delta p will be equal to m delta v is greater or equal to h cross divided by 2 delta x naught, and delta v is h cross divided by 2 m delta x naught. Okay, so from here we got the velocity. Now you know velocity and time are related, right? So delta x equal to t delta v, right? So delta x is equal to t delta v. Okay, velocity is displacement by time. How do you get this? Is velocity is equal to displacement by time. I have just used that relation, and is equal to h cross. You can put the value of delta t here, h cross t divided by 2m delta x naught. Okay, now your delta x is greater or equal to 1. Now h cross is already given to you, 1.05 into 10 to the power minus of 34. Okay, or you can express in terms of h by 2 pi. Either way, it's the same. Okay, here I have just substituted the value of h cross or h bar itself. Now time is what? It's 1. It's given to be 100 second, right? So because this is your t naught. Now 2 m is the mass of the proton, which is 1.67 into 10 to the power minus of 27 kg. Okay, that is given to you. And finally, what is your delta x naught? What is the accuracy? Is 1 into 10 to the power minus of 11 meter. Now what is after time t? Because after 1 second, right, after time t of 1 second, del x is greater or equal to 3.15 into 10 to the power 3 meter. Okay, so the accuracy, I will rather say the accuracy, whatever you measure at time t equal to 0 is given to you, and you have to find out what is the uncertainty in the proton's positions 1 second later. And this is what we find out. We find out that you know, after 1 seconds, that your del x changes to 3.15 into 10 to the power 3 meter. Okay, fine. So from the first, second, and third questions, okay, these are not the fundamental. I will rather say the first thing that we have done in the first few lectures related to your photoelectric effect, Compton effect. Then we comes to uncertainty principles. Okay, next problems I want to solve is related to your atomic spectra. Okay, related to your atomic spectra. I hope you still remembers about in the case of a hydrogen atom, we have find out what is the energy of a hydrogen atom, right? En for the first level, second level, third level, and so on. Okay, so here we will solve the question related to your atomic spectra. Okay, one question related to your atomic spectra. Okay, this might help you in your preparation for the exams. Okay, maybe. Okay, maybe such type of questions will come, or maybe a question from your assignments and that will come. Okay, maybe. Okay, so I'm just review back whatever we have done before, just to brush off many of the formulas. Okay, so the questions is An electron collides an electron collides with a hydrogen atom okay, in its ground state. In its ground state, and excites to a state n equal to 3. How much energy was given to the hydrogen atom in this inelastic condition? Okay, so the kinetic energy here in elastic condition is not kinetic energy is not conserved. Okay, so I hope you remember this energy of hydrogen atom. You remember En is equal to minus of m z square e to the power 4 divided by 8 n square h square epsilon square, and this is equal to minus of 13.6, right, electron volt n z square by n square. I think you still remember this. So we can use the same formula here. The idea is that that your electron collides with the hydrogen. You have a hydrogen in the ground state, and electron is colliding with the hydrogen atom, and then the hydrogen atom will go from your ground state to the excited state. So how much energy the electron gains, I will rather say, or how much energy has to be given to the hydrogen atom in this collision. So idea is that initially you have n equal to 1 state, which is the ground state, to n equal to 3. Okay, so the hydrogen has to go when the electron collides to the hydrogen atom jumps from your ground state to the first excited, not to the first excited, to the higher, to the higher states, with n equal to 3. Okay, so in this case, what we need to do, we can calculate what is the energy difference. Energy difference is what? Is EF minus EI. And this EF minus EI can be expressed in terms of the known energy that you know. So you can express E1 divided by NF square minus of E1 divided by N of I square. And in this case, you can write E1 1 by NF square minus of 1 divided by NI square. Where do I get this relation? I get this relation from exactly from your the same energy that you already know. En is equal to minus of 13.6 ev z square by n square. Since for a hydrogen atom z equal to 1, so you are worrying only your n term. Okay, so E1 is minus of 13.6, right? It's already and your so this is E1 from your hydrogen atom calculation. Then you also know Ni, which is equal to 1, right, from the ground state. NF goes to 3. Then if you calculate here delta E equal to E1 will be minus of 13.6. Okay, so 1 divided by NF square will be what? 1 by 3 square minus of 1 divided by 1 square, right? And this equal to, and this unit is already in electron volt. Remember, minus 13 is already in electron volt, and this will be equal to 12.1 electron volt. So this much amount of the energy and the difference. Okay, this much amount of energy difference between your excited states minus the ground states of a hydrogen atom. Okay, so just give me 2 to 3 minutes. I'll come back, please. Okay, so thank you for uh, waiting for 2 to 3 minutes. Yeah. So so this is the question number four, which is related to your atomic spectra. Okay. Related to your hydrogen atom. So most of the questions, maybe if it is asked, will be related to find, let's say, find the energy difference between the excited states to the ground states, or what will happen to these how does when you absorb an energy from the electron, how will the ground state goes into the excited state. Now such questions are there, but the main formula remain the same, or the main formula that you will be using in the calculation, more or less it will be remaining this En is equal to mass of 13.6 electron volt z squared by n squared. Now this is the main formula that you will be using in most of the cases. Okay, fine. Okay, now so after after understanding this, what else that you can we can think about, okay, is maybe we can solve one or two questions related to your quantum mechanics. Okay, quantum mechanics, which is related to your probability, right, which is related to your probability, and which are also related to your wave function. Okay, one or two problems, okay, which I can solve. Okay, so if you remember, Nata, from your quantum mechanics, we were talking about the wave function psi. Okay, and from the wave function psi, we also talks about what is the probability which is related to your psi square, right? Which is related to your psi square, and from there we also calculate what is your expectation value. Let's say expectation value of x, which is also equal to something like x psi square, and let's say dx. These are the things that we have done before, okay, that we have seen before. And to suppose what is the probability of finding a particle, we have seen, and this is given by psi square. And what is the expectation value of the position, what is the expectation value of the momentum, that we have already seen. Now in this problem, okay, in this problem we'll just revise, okay, one questions. So one questions, let's say question number one. uh, it says a particle limited to the x-axis has a wave function a of x. Okay, so let me write a particle limited, that means it's limited to the x-axis has has a has a wave function psi equal to a of x. Okay, so the wave function is given to you between x equal to 0 and x is equal to 1. Otherwise, psi equal to 0 otherwise. Okay, I think this problem looks familiar to you. Okay, so if I want to represent this one, I can represent in this form. Okay, so something like, maybe something like particle in a box, something like that. Okay, so at from 0 to a 0 to 1, sorry, not 0 to 1, 0 to 1, you have a wave function, a valid wave function given by a equal to a of x, whereas outside this regions, okay, your wave function is equal to 0. Okay, so that means you cannot find a particle there. Okay, you can find the particle only in the position between x is equal to 0. I can write here maybe x between 0 and 1, whereas other than that you cannot find a particle. So okay, so that is the idea. So the question is, find the probability that the particle can be found. Okay, so find the probability, okay, find the probability that the particle can be found between x equal to 0.45 to x is equal to 0.55. So we have a region 0 to 1 in which the particle can exist. And the question is find the probability that a particle can are found in between 0.45 to 0.55. Okay, so that is the question. So how do we do that? We use this the formula which we know that probability is in fact equal to integration from initial position to the final position of chi square d of x, right? So this is what we have done also, that the probability is related to chi square. And in this case, what is the position of x1? x1 is 0.45 and x2 is 0.55. And what is chi? Chi is a of x whole square, since it's chi square, and this is the x. So what I can write is that I can take it out a constant term a square, and x square integration will become to x cubed by 3, 0.45 your lower limit, and upper limit is 0.55. And now what do we get? We get a square into 0.0251, which is equal to 0.0251 a square. Okay, so what is the probability? The probability is 0.025 into a square. Okay, fine. So this is also one of the problems that we did before, right? This is also the problem that we have done before on a particle in a box. Now another questions here itself. Another questions here itself is find the expectation value of the particle's position. Now we have to find out the particles. Find the expectation value delta x of the particle's position. Particle's position. Okay. So how do we do that? I'll write it on the sides. Your expectation value let's say x is equal to x chi of square d of x, right? This is the expectation value. So what I will do is I will solve here. I will solve your expectation value x is equal to, what is the integration limit from 0 to 1, because that is your box length 0 to 1, and x chi square is again a of x whole square d of x, right? Now you can take the constant square a square outside, so you get 0 to 1. Now you get x cube d of x will be equal to a square, and then integration of x cube will be x4 by 4 from 0 to 1, which will be equal to a square by 4. Right? So from there, I think this from there we know that what is the what is the probability of finding the particle. Okay, what is the expectation value? Okay, what is the expectation value? And using the simple direct formulas. Okay, this is okay. Fine. So till now we have solved problems related to your photoelectric effect, Compton effect, right, and also atomic spectra, and also uncertainty principle also, right? So atomic spectra, and again we have jumped now to quantum mechanics, which is related to probability. Okay, so for those who just joined just now, okay, so let me just brief back what we have done. So these classes, okay, is related to whatever we have done before. Is just a reminder of a few problems, just to brush back whatever we have solved long time back. Okay, so first question, what we did, what we solved was related to your photoelectric effect, in which we used that h mu, the energy of h mu is equal to the work function plus the kinetic energy of the photoelectrons. Okay, so this from the photoelectric effect, this formula here, which is like very important. Now from there we also solve problems related to your Compton effect, which says that your scattered photon when it incident on uh, let's see electron's address when it's scattered, let's say from a target or from the electron address. I will rather say from if there is an electron address and you pass your the x-rays with, let's say, with wavelength the lambda, and then the scattered wavelength lambda prime is not the same as lambda. That is what this formula is all about. Lambda prime minus of lambda is equal to h by mac 1 minus cos phi, and also depends upon your the angle of the scattered angle also. Okay, then after that, what did we solve? We jumped to your uncertainty principle, okay, which is also a very well known formula. Del x dot del p is greater or equal to h cross divided by 2. And here the question is, suppose if you know the uncertainty or the positions of a proton at t equal to 0, what is the uncertainty at a later time, 1 second later? Okay, so that is a question. So what did we solve? We make use of the uncertainty principle. Del x dot del p is greater or equal to h cross divided by 2, and we end up to the conclusion, or we rearrange your del x the del p into the velocity into time. Okay, then you substitute what is the time equal to 1 second, and finally you will get and what is the uncertainty in the position at a time 1 second later. Okay, fine. Now after that, what else did we do? We jumped to the atomic spectra. Okay, atomic spectra also uh, we mostly solve problems related to a hydrogen atom before, in which the energy, the velocity, the radius of the hydrogen atom is known. Okay, and the energy, we remember, is given by this form: E is equal to minus of mz square e to the power 4 but by 8 n square h square epsilon square, and your energy E is in fact minus 13.6 electron volt z square by n square. And in this problem, what happens that you have to find out what is the energy, okay, when the hydrogen atom goes from your ground state to the excited state when an electron collides. Okay, when the electron collides with hydrogen atom, the hydrogen atom goes from the ground state to the excited state. So what is that energy, okay, from the ground state to the excited state? And we use of this formula, we just calculate what is the energy difference between your excited state and your ground state, and that is already given to you. What is your initial ground state, n is equal to 1, and your final state also, which is equal to nf is equal to 3 in this case. So, and you found out to be the energy is equal to 12.1 electron volt. Okay. Now after that, we jump to quantum mechanics. Okay, particle in a box, in which you are sure that the particle is in between, let's say in this case 0 to 1, and then outside of that your particle is not exist or does not exist. Okay, in such cases, okay, it's given the wave function, and you have to find out what is the probability in between, in such cases, in between 0.45 to 0.55 according to these questions. And also we have to find out what is the expectation and the value of finding the positions. Okay, find the expectation value of the particle's position. Okay, so I hope you get what we are going through. Okay, so now I'll solve one more problems related to this particle in the box. Okay, yeah, I'll solve one more problems related to this. So the other question is that find the probability that a particle trapped in a box L wide can be formed between 0.4 L 45 L to 0.55 L for the ground and the first excited states. Okay, so the first questions, and the first questions, the probability is, or not the probability, the wave function is already given to you to be ax, but here it's clearly mentioned that find the probability that a particle trap in a box L wide can be found between 0.45 L to 0.55 L for the ground and first excited states. So in this problem also it is the same. Okay, in this problem also we can follow the same like in the last questions. Okay, we can we have to write what is the wave function. The wave function of our particle in the box is given by root 2 by L sine of n pi by L x, right? This is what we know, the wave function. Now the probability between x1 comma of x2 that we have already known from x1 to x2 of psi square d of x, this we already know. And now if we substitute this wave function psi from this to this, then what happens, you can get something like 2 by L integration from x1 to x2 sine square n pi by L x d of x, right? Then what you need to do is that you put out what is the value of your x1 and x2. So if you do the integration from here, you can write something like x by L minus of 1 by 2 n pi sine of 2 n pi by L x from x1 to x2. How do I get this integration? You have to convert sine square in terms of cos. Okay, so when you convert sine square in terms of cos, you will not get this integration. Now then it becoming more clear now. Okay, so what is the first x, what is the ground state, what is the first excitation? So for ground state, what happens, x1 is given to you to be 0.45 L, that is already given the questions. X2 is also equal to 0.55 L, correct? And for ground state, n equal to 1. And in such cases, what is your probability? Probability for your ground state is equal to what? Is equal to, you substitute what is the value of x1, what is the value of x2, and what is the value of n equal to 1 in your I will name it as equation number 1. Then you will get 0.198, which is equal to 19.8%. Okay, you just need to substitute what is the value of x1 in the integration in the equation 1, in the integration in your equation 1, x2 also, and the value of your n is equal to 1, then you will get the probability of the ground state. Now for the first excited state, what is n? N will be equal to, yeah, n is equal to 2, right? So for the first excited state, n will be equal to 2, and in such cases, what is your probability? Your probability will be equal to 0.0065, which is equal to 0.65%. Okay, so first thing that comes into your mind, you will see that the probability of the ground state is much higher than the probability of getting in the first excited states, right? So this shows that your the particle are most likely in the ground state than in your first excited states. Okay, or you are most likely get to find the particle in the ground state than in the excited states. Okay, so I hope I think of these problems related to your particle in the box should be I think should be okay. I think should be enough. Maybe I can solve one or two more problems. Okay, then maybe we can stop. Okay, okay, fine. Now also before we go ahead, okay, we can like we have done last class. Okay, so let me just go back to last class, whatever we solved, which is related to your sorry, yeah. So this so I will solve one problems related to your your nuclear physics also. Okay, so I think this is very important to remember this classification of particles which we have discussed yesterday. Okay, how do we classify your hadrons, your leptons, and how do we classify your mesons and baryons, and how do we solve the conservation of lepton, conservation of baryon, strangeness, quarks. I think this is also one of the like fundamental things that we need to know what are, how do we classify the fundamental particles or the elemental particles in terms of different classes. Okay, now why I'm saying this is because, sorry, is because I will solve one problems now related to your uh, related to your nuclear structures. Okay, related to your nuclear structure. Not nuclear structure, maybe nuclear, yeah, nuclear, yeah, your nuclear structure, we can say it. Okay, so what is the question? The question is that show that pion decay, comma mu1 decay and pair production conserve the lepton number and L mu. Okay, this is what we have to find out. So yeah, so how do we know that whether the lepton number or mu1, especially the lepton numbers, are conserved or not? So what we have to do is we have to find out what is the lepton numbers on the left hand side of the reaction and what is the lepton number on the right hand side of the equation. And if they are the same, then it is conserved. Okay, similarly for energy, similarly for charge, right? Similarly for baryon number, whatever we have done last class. Similarly, all of those things we have to make sure that your left hand side, which is the initial reaction, and the final reaction should be the same. Okay, that is what it is. Now so let's start first, which is the pion case. Okay, so the first thing, which is pion decay. So here, okay, the reaction is given due to be pi minus goes to mu minus plus anti-neutrino. Okay, mu1 anti-neutrino. So you have to check whether your your electron lepton numbers or mu1 lepton numbers are conserved or not. So in this case, what happens is that since there is only mu1, we are mostly interested only your mu1 lepton number. So L mu is pion a lepton? No, right? It's not. It is a mesons. Pion is a mesons. So in that case, what is your lepton number? 0. Now mu1 is a lepton number, and since this is a lepton number, is given by +1. And what is anti-neutrino? Since it is an anti-neutrino, instead of +1, it will be becoming -1. So now your delta L mu is exactly equal to 0. Correct? Is equal to 0. That in such cases, your mu1 lepton numbers is conserved because the difference is equal to 0. Correct? Now we'll talk the second. Let me write here, this is a pion decay. Now we will move to the second, which is called as a mu1 decay. What happens to mu1 decay? I can write mu1, mu negative goes to electron plus neutrino plus anti-electron neutrino. I mean electron anti-neutrino. Okay, so how do we find out this this conservation numbers? Again, we will do the same thing. We will do the same thing by finding out what is L of electron. Since this is a mu1, we have 0. It is an electron, so electron lepton number will be 1, and this will be 0 because since it is not an electron, and this will be equal to, since it is an anti-neutrino, instead of +1 will be becoming -1. So here your delta L electron is also equal to 0, which is conserved. Now L mu, the same thing. Le is for electron and L mu is for your mu1. So L mu in the left hand side, now since it's a mu1, you have 1, and electrons, since it is electron, so L mu for electron will be equal to 0, and this case for your mu1 neutrino again will be +1, and for your anti-neutrino will be equal to 0. So here also del L mu will be, left hand side is equal to 1, right hand side equal to 1, so the difference will be equal to 0. So this is also conserved. Okay, fine. Now the last thing, which is the pair production. Okay, pair production. So pair production is gamma, which goes to electron plus your positron. So in this case, your electron lepton number will be equal to what? Gamma is not a lepton, so it will be equal to 0, whereas your electron will be plus 1 since it's lepton number. But positron, since it is the antiparticle of the electron, it will become to minus 1. So here delta electron is also equal to 0. Okay, so it is conserved. So since, remember, since that your initial reactions and the final products, I can say your initial reactants and the final products are the same, and both the lepton number, okay, for your lepton numbers for electron, lepton numbers for muon, okay, that is why you should say that it is the conservations is valid and the reactions are allowed. Okay, and we have also solved questions yesterday, also many questions in which, in order to find out also what are the missing elements, okay, based on the conservation laws, we can find out that what are the elements that are allowed. Okay, what are the missing elements that are allowed in the reactions? Okay, that we also that we have seen in the yesterday's class. Okay, so we can take a rest of 2 minutes. Okay, I will start the next two questions, then I will stop. Okay, so we can take a rest of 2 minutes. Okay, a break of 2 minutes, then I will come back after 2 minutes. Okay, so let's continue the remaining two problems. Then I will stop after solving the two problems. Okay, so the next questions that I want to solve is related to your binding energy. Right? You know that I have given you the formula that the binding energy, let's see, EB is equal to atomic number, mass of the hydrogen, plus number of neutrons, the mass of neutron, minus the mass of your element. Right, this is into 931.49 MeV per U. Okay, so how do you get this binding energy? You take the mass defect between your reactants and the products, and you multiply with using the Einstein relation, delta E is equal to mc square, or E is equal to mc square. So if you use this formula, okay, and convert whatever the mass in terms of 91.49 MeV, you can get the energy release, okay, released in the reaction. Or as we have just in the last two classes, as we have just said, that if Q is greater than 0, it will be released. Otherwise, if Q value is less than 0, it will be absorbed. Okay, so that is what we have seen. Now let's solve one question from this, which says that the binding energy, the binding energy binding energy of a neon isotope of a neon isotope 20 Ne10 is 160.647 MeV. Find its atomic mass. Okay, here is different. Okay, the binding energy is given to you. It's not that you have to find the binding energy. The binding energy is given to you, but you have to find the atomic mass. Okay, so so you just need to reverse this reaction, which is already given. So what you need to do is that you can write your reaction now is M A x Z in terms of mass is equal to Z. This remain the same, mass of hydrogen or mass of the proton, plus N, mass of the neutron, okay, minus of EB by 931. Instead of multiply, you have to divide 931.49 MeV by U. Okay, so for a neon, what happens is that your for a neon, your Z is 10, and your N, which is equal to A minus of Z, is also equal to 10. And what is the mass? Mass of your 20 neon 10 will be equal to what? Will be equal to Z is 10 into the mass of the hydrogen is 1.007825 U. Most of the time you don't need to worry, mass of the hydrogen should be given to you. Okay, and sorry, so 25 U, okay, plus neutron into the mass of a neutron, which is again 1.008665, okay, minus what? EB is already given you 160.647 in terms of MeV, divided by 931.49 MeV. And so how do we what do we get here? We get here, you just multiply this and then this, and divide, evaluate, you will get 19.992. Okay, so this is the formula of your neon. Okay, the atomic mass of a neon, by knowing the binding energy. Or you can do the other way around also. You can, if you know the atomic mass, you can calculate the mass effect. You can get the binding energy. That is what we have done last class, but this is the just the reverse of it. Instead of the binding energy, you calculate what is the atomic mass, knowing the binding energy. Okay, so maybe one last questions I will solve, and then maybe we can stop the sessions. Okay, so maybe last questions what I want to solve is maybe related to your radioactive decay. radioactive decay. And radioactive decay, you still you remember the formulas, or the uh, it is given by n equal to n naught e to the power minus of lambda t, right? Then so the remaining atoms, uh, or the atoms which left undecayed, okay, is given by n naught, which is the order atoms e to the power minus of lambda t. Or you remember this, the rate of disintegration for a radioactive nuclei is, this is n naught here, and this is your time t. It follows your exponential decay, right? And is equal to n naught e to the power minus of lambda t. Now, in last class we calculate what is the lifetime, what is the lifetime, what is the average time, right? So in this case, one questions which is also similar is find the activity, find the activity of 1 milligrams of radon. Radon is also is radioactive, of radon 222 Rn, whose atomic mass is 222U, and T half equal to 3.82 days. Okay, so what is activity? Activity is, activity is given as R is equal to something like lambda into n, where lambda is a disintegration constant. Okay, so or you can also write is equal to minus of dn divided by dt. Okay, it's the same thing. And now, since you know the t half, you have to find out what is the value of lambda, okay, and you have to find out what is the value of n, and then you can solve what is your activity. I represent this activity to be r. Okay, now your lambda is equal, in terms of half-life, is 0.693 into your t half. This is what we know, 0.693, and t half is given you in terms of days. We can express in terms of seconds, so we can write 3.82, and in terms of seconds, this is 3.82 into 86400, which is equal to 2.11 into 10 to the power minus of 6 per second. So how do we convert days in terms of seconds? You just multiply 24 hours into 60 minutes into 60 seconds. You will be able to convert this 8600. So you need to convert from days to seconds. So now your lambda is in terms of second per second. Okay. Now you know the value of lambda. Now you have to find out what is the value of n, right? So n, the number of, I can say the number n, I will rather say the number n of atoms in 1 milligram of radon of Rn222 is what? How do we get the value of number of atoms? N is equal to, you take what is 1 milligram. 1 milligram is 1 into 10 to the power minus 6 kg. Okay, if you represent in kg, divided by your atomic mass 222 U into 1.67 into 10 to the power minus of 27 kg and U. If you want to express in terms of kg, you have to multiply 1.67 into 10 to the power minus of 27 kg per U. Okay, now once you do that, you will get the number of atoms n to be 2.71 into 10 to the power 18 atoms. So the idea is that you have the mass 1 milligram divided by your atomic mass, okay, and since this is 2, you convert in terms of kg, that is 1.67 into 10 to the power minus of 27 kg, okay, and you will get cancelled either way. Now you get what is the value of lambda, you get the value of n, then activity R is equal to simply lambda n. So lambda is equal to 2.11 into 10 to the power minus 6, and to n 2.71 into 10 to the power 18. So you will get something like 5.7 into 10 to the power 12 decays per second. Okay, so the activity is 5.7 10 to the power 10 to the power 12 decay per second. Okay, so these are all the problems which I just want to remind back, or just want to solve a few of the problems which we have already seen before. Okay, similar problems which we have already solved before. Okay, in today's class what we did is we just solve again, just remind some of the questions which is related to you. Okay, and other than this there are also many questions which which I cannot solve here. Okay, many places, like from your quantum mechanics we also have your hydrogen atoms. Okay, your hydrogen atoms, your harmonic oscillators are the simple problems which are also there. Okay, those I cannot solve like all of them. So I just pick out some of them. I mean, I've just picked some of these problems which I have solved just now. And if you want to solve more problems, I think most of the reference books I have already given to you before. Okay, what I used to follow is Arthur Beezer. Okay, Concept of Modern Physics, Arthur Beezer. This is also the books which that I usually follow. And your Quantum Mechanics by ZD. Quantum Mechanics by ZD is also what I used to follow. Okay, so other than this, also you also have your solid state physics, right, by Kittel. Okay, here we have not in today's class we have not solved problems related to your solid state physics. Like I still remember we solved some partition function and so on. Okay, so those related questions can also be found from this the book Solid State Physics by Kettle. And yeah, so I think this is the last sessions that that I'm going to take some tutorials, okay, for these sessions. Okay, so if you have any questions which you feel, you can always mail. Okay, we can always solve some more questions if you feel like. Okay, but I think according to the schedule, I think this is my last sessions for this for your course. So thank you so much for attending the classes. And any questions, always feel free to mail me. Okay, I'm willing to solve some more questions depending on the type of questions which you need help or which you want to solve. Okay, other than that, I would like to conclude my classes here. Thank you so much. And all the these tutorials, also videos will be uploaded in the YouTube. And also the notes which the solved notes also I will upload in the drive. Okay, so thank you so much. See you soon. Divide with, okay, I think is equal to, or what is the baryon number for each quark that I have already given to photo. So now lambda prime is the scattered and second. Also before, okay, is given by n naught